Bonjour à tous. Mon nom est Michel Tremblay. Je suis le président de l'Académie des sciences à la Société royale du Canada. Pas pour très longtemps. Et je finis mon mandat, en fait, aujourd'hui. Nous allons bienvenue à la conférence Romanowski. The Miroslav Romanowski Medal, an annual lecture, was established in 1994 at the generous bequest of the estate of internationally renowned metrologist Miroslav Romanowski. Metrologist, I send you for many of you that you may not, so think about this, what it means. What is the science of metrology? The recipients selected for this award are recognized for having made significant contribution to the resolution of scientific aspects of environmental problems or for important improvement to the quality of an ecosystem in all aspects, terrestrial, atmospheric, and aqueous, brought about by scientific means. And this is important in our days, that this is a scientific process. Ce prix vise à reconnaître une contribution importante à l'explication scientifique de problèmes environnementaux ou à reconnaître l'amélioration notable par des moyens scientifiques de la qualité d'un écosystème sous ses aspects terrestres, atmosphériques et aquatiques. Because this year's lecture is being presented by Dr. Catherine Mulligan, it makes all the sense in the world that Concordia University is supporting this weekend of celebration, as well as this scientific lecture, since Dr. Mulligan is from Concordia University. We thank them. The RSC is grateful to Concordia University for its continued support, especially for this lecture today. Tim Evans est vice-recteur à la recherche, à l'innovation et au rayonnement à l'Université Concordia. Il est titulaire d'un diplôme de médecine de l'Université McMaster, mon alma mater aussi, et d'un doctorat en agroéconomie de l'Université Oxford, où il a été boursier Rhodes. Before joining Concordia, Dr. Evans was the inaugural director and associate dean of the School of Population and Global Health at McGill University, where he also served as associate vice president of global policy and innovation. He was also executive director of Canada COVID-19 Immunity Task, and as you know, this was the task force was an important contribution to Canada during these years. He held also senior leadership roles at the World Bank, the World Health Organization, and the BRAC University. Throughout his career, Dr. Evans has played a key role in advancing global health initiatives. He co-founded Gavi, the Vaccine Alliance, led the World Health Organization Commission on Social Determinant of Health, and worked to expand access to HIV treatment and midwifery training in Bangladesh. Je vais être modérateur de la rencontre après la présentation du Dr. Mulligan. I now invite you to join me in welcoming Dr. Tim Evans to the podium. Dr. Evans, welcome.
Good afternoon, everyone, et bon appétit. It's a great pleasure to be here today at the RSC's celebration of excellence and engagement. And I want to begin by extending warm thanks to Dr. Michel Tremblay for the warm introduction and for your terrific leadership as president of the Academy of Science. Nous sommes ravis de participer à ce rassemblement qui réunit les plus grands chercheurs, chercheuses, artistes et universitaires du Canada, tous et toutes unis par la quête de savoir, de découverte et d'un impact concret. The RSC, as you all know, plays an incredibly important role in stewarding the research enterprise in our country, and I'm sure it won't be a hard argument to make, but there's probably been no time where it's been more important to try and steward that scientific enterprise to address a very diverse range of challenges that are in front of us, that are moving very quickly, that are packed with uncertainty, and that unite us across borders, even though many, especially politicians, may be unwilling to recognize that. The RC, by supporting cross-disciplinary collaboration and connecting scholars across generations and regions, helps ensure Canadian research will make meaningful contributions to understanding and to finding innovative ways to address the complex challenges of our time. It's my honor to introduce today's speaker, Dr. Catherine Mulligan, who is receiving the Miroslav Romanowski Medal in 2024 for her pioneering work in sustainable environmental engineering. Catherine's research on biosurfactants and soil remediation has transformed decontamination science, offering greener, safer solutions for water and soil contaminated by heavy metals and pollutants. Dr. Mulligan's work has a direct impact on the challenges we're facing today, not only in Canada, but around the world. And with the COP30 currently convening in Brazil, global attention is once again focused on sustainability. And her research exemplifies how practical solutions in engineering and environmental science complement policy efforts and inform community action worldwide. Over a career spanning more than 4 decades in government, industry, and academia, Dr. Mulligan has supervised more than 75 graduate students, authored over 140 refereed papers, holds 3 patents, and she founded the Concordia Institute for Water, Energy, and Sustainable Systems, which I had the opportunity to visit earlier this year, having just arrived at Concordia, which is training the next generation of engineers to implement sustainable practices. A little bit of a story about Catherine that she may not know that I'm going to reveal, but I did a little bit of homework, and she really loves field research. And so she had her team on a lake in northern Quebec. It was a lovely sunny day when they went out. They claimed they were working on eutrophic water remediation by geotextile filtration. However, the sun disappeared, and they decided they had to get back. But as they were packing up, the weather changed dramatically, and there was a really very torrential rainstorm that took them over. They were concerned they might be stuck out there, but Catherine said, no, get in the car, I'm driving. And so she guided the wheel and safely got them all back to Montreal that evening through the storm. And I think this little anecdote is Catherine to the core. Steady, fearless, and completely dedicated to her team. Her mentorship and leadership reflect the very best of what Concordia values: integrity, innovation, and care for the people she works with. Care for paper, too. So Concordia, I want to express our deep appreciation to the Royal Society of Canada for its leadership, vision, and mentorship. Over the years, Concordia has been proud to see members of our community participate with you as fellows and medal recipients, reflecting the shared commitment to research excellence and societal impact. Le travail de la société renforce l'excellence de la recherche canadienne, favorise la collaboration entre les disciplines et amplifie l'impact des travaux de recherche et de création au bénéfice de la société. So, without further ado, it's my absolute pleasure to welcome Dr. Catherine Mulligan to the stage. Catherine?
So thank you very much. That storm actually was a side part of a tornado actually that had arrived in Montreal that day, so which I found out afterwards. So it was a bit of one of these white knuckle rides back to Montreal that day. Anyway, so thank you very much, Tim, for that excellent introduction, and I also thank the Royal Society for giving me the opportunity to receive the medal and also to give the lecture today. Je suis vraiment heureuse d'être ici, mais je vais faire la présentation en anglais. Mais par contre, s'il y avait des questions plus tard en français, je peux les écrire. Today I'm talking about the geo-environment, which is probably something that you haven't really thought about. People know about water, people know about air, so I thought, well, maybe we need to get people a little bit more conscious of the soil environment and so on. So this is what I will talk about today. So how my talk is basically lined out. We'll do a bit of an introduction, of course. What is the geo-environment? How is it important? What are some of the impacts that humans do to the geo-environment? What are some of the practices to protect it? So I'll talk a little bit in general and also some of my specific research that we're doing. And also how to restore it. And then finally, I'll make some concluding remarks at the very end. So first of all, I wanted to start it off with the land acknowledgement. So basically saying that Montreal is located on unceded Indigenous lands. The Kainai Nation is recognized as the custodians of the lands and the waters on which we gather today. Tiohtià:ke, Montreal, is historically known as a gathering place for many First Nations. And so I thought it was important to start off, of course, with this, but also to emphasize the importance of the land to the Indigenous people. And so this is exactly what I wanted to focus on a little bit, just to start off with, saying that they are stewards of the land through various traditional teachings, which they pass on from one generation to another. They have a deep reverence for the land, for the nature, and the interconnectedness. They use it as the basis of a storytelling, ceremony, and a profound connection to the ancestral lands. And it supports their identity, social culture, and socio-spiritual systems, as well as physical, emotional, mental, and spiritual health and well-being. So due to this reliance on the land, for them, of course, they get the support from the wildlife, the plants, the water, soil, environment, basically is very, very important, and so it must be clean, and it must be uncontaminated. So this is exactly what we will be talking about today, the geo-environment. So the geo-environment itself, in reality, is the mixture of everything. So it's kind of the interface between water and soil, and the soil and the air environment. So it includes, of course, the atmosphere, the hydrosphere being the water, the geosphere, looking at the soil environment itself, the biosphere, of course, all the microorganisms, the plants, and everything that's involved in it, and of course the anthroposphere, which we are part of it. So in reality, the geo-environmental is basically a primary resource for many, many things. And so we cannot live without a good geo-environment. So to meet these goals of sustainability, we need to conserve the resources there and to mitigate any of the impacts and manage the impacts as much as possible. So of course we've seen the various pressures due to climate change most recently. We've seen a lot of floodings. We've seen fires that have been out of control this particular summer. We've looked at other places have droughts, and of course these all are due to this changing climate changing. So the temperature, of course, is being increased from about 1 to like 1.5 degrees. Very soon, and of course, as I say, it's changing all of these precipitation patterns. Like even the lake that Tim was mentioning there before was very low because there's very, very little rain that happened during this summer. So this also exacerbates the pollution aspects as well. And we've seen that you can have many, many different impacts, of course, depending on how much the temperature is going to be rising. So if we're looking at only 1 degree, there are some changes, like you might see some species start to be extinct that are very, very sensitive to climate change. Some of the glaciers are starting to go, some of the sea levels are starting to rise, and so on. And then, of course, we will have, if the temperatures get to a very, very extreme 5-degree changes, then you start to see very dramatic changes that we may have to move different places, and so on and so on. So these also are presenting various challenges to the geo-environment. So definitely elders, Indigenous leaders advise us that really we're at this tipping point because of this climate change. And so we need to listen to the First Nations, the Inuit, the Métis, and we need to urge policymakers and not do the reversal that's starting to happen really now. We as academics need to continue our work, and business leaders as well. And everybody needs to get on board with that. So we've seen the sustainability goals, of course, that the UN has come up with. The land, of course, is one of the major ones. As we've seen here, the life on the land is definitely one of the major goals that needs to be preserved and so on. And of course, you see related to that is the clean water and other aspects. So the geo-environment is a resource. Is a habitat for many, many different organisms, for anything from earthworms to microorganisms and things like this. We use the soil for agriculture, for growing food, and so on. It has a tremendous influence on the groundwater itself. We get minerals, hydrocarbons, fuel, and so on from the geoenvironment. We also can take advantage of it for like geothermal energy as well. And also, if you're looking at the infrastructure in a city, of course, everything is based, the soil is the base of soil. The soil is the foundation, or all the roads, the buildings, and everything like this. If you don't have a good foundation, you don't have a good building, right? So, we're starting to see, hopefully, a little bit that, okay, it is a very important. So in terms of food security, definitely we need to maintain the quality of the soil to be able to have good crops and so on. The thing that maybe people don't think about as much is that it is actually a good source of sequestration of carbon. So you have the organic matter that's in the soil, and it can help to capture a lot of the CO2 that's there. So it is definitely a help. The soil also is a good protector for the water environment as well. Any rain and things like this, the pollutants and so on, will pass through the soil. And the soil, if it's a good retention of the capability, it will protect the groundwater quality. It can also protect the surface water as well, which we will see a little bit. And of course, we have the biodiversity. It can help to maintain that. And of course, there are many economic benefits that we've started to talk about. So some of the polluting activities. So we have industrialization. So of course you have all the waste that are being produced. You have the wastewaters that are discharged from various industries, and so on and so on. The urban environment. You have the landfills and so on. That holds all of the waste materials and so on. You have the water and the wastewaters and things like this that are coming from this thing. From agricultural, we'll talk a little bit about that, but the fertilizers, the herbicides, and things like this that are put on the land, of course, might not stay on the land. You have the resources industry, which we will also talk a little bit about, which generate various tailings and ponds and things like this that could cause some issues with the environment. And if you have the forestry industries, if you take out too much of the trees, you leave the soil possibility of erosion and so on, and losing the good quality soils. So all of these are different types of contaminants. You end up with contaminated land. We call them brownfields if they're used and been contaminated. It's no longer it no longer has the original properties anymore. So we will call these brownfields that have these type of characteristics. The land could be degraded, the groundwater can be contaminated, and it obviously can have effects on public health because of the consumption of contaminated groundwaters. Contaminants could be increased in the water environment, so changing the pH and things like this, and then of course the species could be changed as well. So soil itself is actually very complex. This looks very simple here, but basically, the majority, of course, are the mineral materials that make up the soil. A lot of it's water, depending, of course, on how much it's rained and so on. And then, of course, what's not filled with water has air. And you'll have a certain amount of organics that are there because of the decrease of like leaves, of course, that fall, especially in the fall. So you have the leaves, you have anything that's died and will start decomposing and so on, so it will form the organic content of the soil. Soil itself also is very challenging to do research on or to do remediation work, because basically anytime you're going to do a site, it's always different because the soil varies so much from place to place. So as you can see, you can have clay materials, you can have sandy materials, you can have maybe one place is over there like this, and another place is fairly very different just over here. So the particle size makes a big difference. The composition of the soil is also various. So depending on where you are in the horizon, on the top of the soil, or further down, which is the more, maybe most likely similar to the parent material, so then you end up with the original rock material that the soil had originated from. So water itself also is very, we don't have a lot of fresh water. Basically, only 2.5% of all water is fresh water. So the fresh water, of course, which we can readily drink and so on without having to do the treatment, desalinations that you would have to do for ocean water. So only 2.5% of all water on Earth is fresh water. Of that, 70% is actually in snow, ice, and glaciers and so on, so it's not really accessible. Another 30% almost is groundwater. And then the remaining small percentage is from lakes, ponds, and rivers, and things like this. So really, we need to look after this resource. So water itself, as I was saying, we're looking at the soil, but this interaction, as I say, is very important. And of course, looking at the hydrological cycle, you're looking at the fact that it will rain, it will land on the land, it will be run off. If it's been raining a lot, whatever, it won't saturate through the thing, it will run off, and then which could run off into lakes and rivers and things like this. If it's not so saturated, then it will seep through and it will go into the groundwater itself. So it's always the replenishment of the groundwater and so on. So as you see, there's a big interaction of the water and the soil. And so that's important because in reality, the water is what transports the contaminants once again on the land. So is it contamination of sites and soil a big problem? Well, this is only federally owned land. This is only that. So apart from that, of course, you get all the provincial, the municipal lands and all of the things, but this is only the federally owned lands. And as you see, about 2,600, 2,700 sites are undergoing assessment at this point. Another 1,000 are actively being remediated, and another 300 are being totally monitored at this point just to make sure to see what happens with the contaminants at the particular site. And another almost 1,000 are going to be assessed in the near future. So you can see that it is a quite significant issue even in Canada. So you can have contaminants from many different types of sources. We even have naturally contaminants of natural origin. We have what we consider non-point source and point source, which I will also mention. So these are some of the contaminations possible. So you could have like a landfill. And so if it's properly engineered, this shouldn't be a significantly problem, but sometimes there's still little punctures and things like this in the liners at the bottom of the landfill. So you can have some leachates. If it's not a properly engineered landfill, just a regular dump, then it could be a significant problem that you can have pollutants here. You could have people just dumping contaminants on the ground. You can have underground storage tanks. So say, for example, you have a gas station. Typically, you have the gasoline stored underneath the ground, and typically there could be some corrosion in the tanks and it could be leaking. So often you'll see, like if there's a conversion of a site from a gasoline station to a condo project, you'll see that they'll usually have to do remediation at that particular site because of the contamination from these leaking tanks. And as you see here, that of course it can get into the groundwater. Just going back for a second. So the groundwater being at the very bottom. Okay, so many types of pollutants could be there. Different metals, as you see, hydrocarbons, oil, and things like this. So depending on the type of contaminant will determine how are we going to deal with this contamination once it gets into the environment? You'll have to see what kind of transport, what happens to these contaminants. Is it going to move? Is it going to stay there? Whatever. These are some of the understandings that got to be gained. And of course, ultimately, if you want to remediate this particular site, then you want to make sure that it's going to get clean, and hopefully as clean as possible, and ultimately restored to the original status. But often that's not done just according to the regulations. That's what's really followed. Okay, so I mentioned about organic, originally the natural contaminants can also be present. So arsenic is a key example of a natural contaminant. So what happens is that sometimes the soil can leach out the natural minerals that are in the soil. So particular types of contaminants might have too much high arsenic levels, and they can get into the groundwater. People drink the groundwater, and then they've been affected quite substantially in certain countries like India, Bangladesh, and even in Canada to a certain extent, particularly near mining sites and so on. A lot of the gold also contains arsenic, so that can be also a source of problem. And although Canada is not shown as having arsenic, but there is some places. Okay, so, but a lot of the contamination, oops, sorry, a little bit too fast there, as I was saying, is from industry, urbanization, resources, which I'll kind of go through each a little bit. As these are what we call point sources, so there's a known origin of the contamination. Or we have certain agricultural activities, so putting in farm waste, using soil erosion, fertilizers, insecticides, things like this. They're usually spread out quite substantially over the soil, and thus you have these what we consider as non-point sources. But regardless of what kind of contamination, they still can get into the surface water or into the groundwater. So just in terms of agricultural activities, you can add compost or sewage sludges or fertilizers or manure and things like this. So all of these are either organic or inorganic fertilizers. So even regardless, even if it's an organic fertilizer, if you're still putting too much nitrogen and it still contains nitrogen and phosphorus. So even if you're adding too much of these materials, they can still get onto the soil, run off into the lakes and the rivers, or into the groundwater and cause various issues. So this is just the kind of the schematic if you do that. So if you have these organic sources, it runs off. It can either go into the groundwater or into the lake. And then if you have too much phosphorus or nitrogen and things like this, then you get algae growing in the water. And then now you get a nice green lake. And so you have an issue. And then it also can be absorbed into the sediment. And so the sediment kind of captures a lot of the phosphorus, but what then can happen is it can be re-released later on. So this is just a picture that I took a long time ago when we did some research in the eastern townships there. So it basically shows you some of the runoff that came from the agricultural fields. And so you see the water is kind of green and very, very turbid. And you're also losing a lot of really good soil as well when you're doing this type of thing. And as you see, there's nothing on the riversides and things like this to capture. So if you had some natural growth of, a little wetland type of things to set up alongside, they could absorb some of these contaminants and avoid some of this runoff going into the river. So, industry. You can have the discharges, of course, into the water. You can seep into the groundwater. And you can also have the air emissions from the particles and things like this. And unfortunately, the fish may disappear after the time, as you just saw. So just looking at some of the pictures from different industries that I visited. Well, this one I didn't visit, but this is from tin mining. So you can see the very extensive water ponds that you can see here and also in the other arrows, you can also see where there's sand and various rejects and residues from the mining industry. This is just some runoff from coal mining tips that are in the UK. So a lot of iron, so causing the rivers to look very brown. And these are some pictures that I took at a gold mining facility. So you can see on the left side, you can see the tailings that's been left to dry over time. But before that, they were as the pond as you see here. And that was my little underground visit, as you can see from the little picture there. So, and in urban aspects, you're looking at various emissions, the solid waste. You can have runoff just maybe from the road surfaces. So just the fact that you have road surfaces, it's actually interfering with the infiltration of the water through the soil into the groundwater. So first of all, you're changing that particular property, and then second of all, you're creating usually runoffs. So you have all of the rubbers, the particles from the tires, the unburnt fuels and things like this, little spills, some antifreeze and all of this type of stuff that also can cause issues as well. Okay, so now I've done all the nasty stuff, saying this is all the things that are happening. Now, what can we do about it? So, first of all, stop doing all that. A lot of these things. Just try to stop putting the pollutants in the environment in the first place. That will help. Try to have various procedures that you can reduce the amount of waste, say for example, that's going into landfills, especially hazardous waste that are going into landfills and things like this. Use different remediation processes, so sometimes I'll go through a few of them, and hopefully we'll be able to restore some of the habitats and things like this to help us to naturally do the purifications of the land. So if you have a site that's contaminated, you have to go through this whole procedures of assessing what's at the site. Is it contaminated or not? Usually you have a very set regulations, depending on, of course, it varies from province to province here in Canada. But usually you look at the regulations, you see, is it contaminated or not? Then, of course, if it's considered as contaminated, then maybe you have to do the cleanup at that particular site. It depends, of course, on what you want to use that land for. If you want to do a redevelopment of your project, you want to do some other building and things like this, you probably will have to regulate it, to adhere to residential regulations, so you want to have the very good quality soil. If you're going to use it for industrial purposes, of course, the quality of the soil doesn't have to be as good. So you also have to look at the cleanup options. What kind of cleanups, what type of technologies could be used, how you do the work, what is it, are you achieving what you want to, and then you have to see, of course, according to how much you did clean up, what can you use the land for. So ultimately, we would like to do the redevelopment as sustainably as possible. And as you see, community input is usually quite important. And of course, you need to have the technology to do it. You need to do the risk management, see how much, the costs and the funding and everything, of course, is definitely important as well. Okay, so these are some examples of, this is a landfill that was in France. And basically, you can see that now they've let it grow to the poppies and things like this. So now it's sort of returned to its natural state after they closed the landfill. This is a closed landfill in the Mississauga area. It's now converted to a golf course. And these are in the east end of Montreal, the Parc Frédéric Bach. So basically, they've converted into a recreational area. So there's a lot of bicycle paths all around it. They have picnic tables and things like this. They are still collecting the biogas that's being produced from the landfill, so they're still using that to some extent. And these little yellow balls there are basically, they've kind of made it kind of fun looking so that kids can be educated on how much gas is being produced. And so you can see the gas monitoring stations around the park itself. So this particular landfill used to have enough gas to fuel about 30,000 houses, for the energy for about 30,000, but now because it's an old landfill, the gas is going down. But these are also reasons why you can't really build on the landfill, because there's still gas production, and also the fact is that you still have settling of the waste and things like this, which could be quite not uniform. So to put a building on it is not a good idea. Okay, so just in general, we weren't very conscious of contaminants and things like this in the past. Now we've moved towards trying to do some waste minimization, reduction, more recycling. We've tried to look at things as a more life cycle concept, so looking at life cycle assessments and things like this. And then finally, of course, we're still doing that, and also looking at sustainability as another parameter that's needed. So, as I was saying, one of the ways of reducing, of course, what will obviously end up in the waste disposal at the very end, is to try to do this cycle of waste, recycling, reuse, and things like this as much as possible. And by doing that as well, you're also reducing the amount of resources that needs to be extracted from the environment, which are going to be finite to begin with. Right? So basically trying to create this circular economy approach. So what type of remediation can be done? One of the cheapest, and unfortunately used still quite often, is just removing the contaminated from the site and sending it to the landfill. So unfortunately, this is still fairly cheap and fairly common to do. You can put other stuff like on top of the contaminated site, or you can do various remediations at the site itself. So whether it be by adding chemicals to immobilize the contaminants there, add chemicals to break the contaminants, biological means to break the contaminants as well, or looking at natural processes, which I'll talk a little bit about. You could also do what we call ex situ remediation too. So whereas I think I have, actually, no, well, I'll go back to that. But you can also do ex situ, where you excavate the soil and bring it somewhere else and do the decontamination somewhere else, and then you could reuse potentially that soil from somewhere. So as I mentioned, you have the in situ right on the site. You don't have to do the transport, so it saves a lot of the transport, the greenhouse gases, and things like this, and it's definitely much more sustainable than the ex situ, where you have to take it out and bring it somewhere else. But sometimes you're forced to do that because you need to use that land that got contaminated, but you need to use the land very quickly. Maybe the ex situ, unfortunately, is the good process. So as I mentioned, there's kind of breaking it down to physical, thermal, and biological. So we want to make sure that the remediation process itself is also sustainable. So although we're doing a cleanup, we're doing a good thing, we've got to make sure that we're not going to be creating other harms on the environment, like using too much energy, too much water, things like this. So there's been some forums that have come up that have been developing guidelines for how do we make a sustainable remediation. So in Europe, we have CLARE, SURF was developed in the USA and the UK. You have green remediation, which I'll mention. And in Canada, there's been efforts, but there are some caveats or some, you get some extra points sometimes if you propose a more green remediation compared to a regular remediation if you're doing some of the remediation on federal lands. Okay, so green remediation is the same. Basically, you want to minimize the amount of materials, waste materials, energy, and impacts on the land, impacts on the water, and on the atmosphere as much as possible. So the ASTM has come up with some frameworks. So looking at doing the size assessment, but the important difference is, because I showed you this framework there before, but basically the difference is that you have these BMPs. So the BMPs are best management practices. So these are starting to think about how to get a better remediation process. So, as I was saying, looking at the waste, looking at the emissions, looking at the water that's used, the energy, and things like this, while you're doing the remediation itself. So, one ultimately very friendly, eco-friendly method is actually taking advantage of all the natural processes that are going on in the soil, and we call this natural attenuation. So, you have microorganisms in the soil, they can do the biodegradation, they can do other things. You have the rain and things like this. So these are natural dispersion and dilution processes and things like this. So the idea is to use some of these natural things that are going on, and hopefully will decrease the contaminant concentration. And also, if you have the microorganisms, they'll break down these toxic components, and hopefully it will get there. Now, unfortunately, it's not what do you call it, the ultimate solution to everything. It's not going to work everywhere. It will depend very much on the soil characteristics. So this is ultimately what you want to choose to have, having the contaminants coming in. They're going to be retained in the soil. Anything being leached out contains very few contaminants. But you'll have to have the right conditions at that particular soil to be able to do this type of process. And so then there's certain evaluations. You look at, is your contaminant decreasing? Do you have any evidence of microbial activities that are going on? Do you have any active of the particular bacteria that can do the degradation processes and things like this? So those are kind of some of the indicators that could be used to see whether, and so then you would have to prove these to the regulators to say, hey, this is a way that we want to be able to do this type of work. So there are different protocols that have been developed. So it works mainly for fuel type of contaminants, but it might also work for other type of contaminants. So there are other type of protocols for metals and things like this. So this is basically the same type of schematic as I showed before, but the difference is you have to do the monitoring, and this is where so you're not physically actually adding any engineering facilities to it, but you're doing wells that you can be able to monitor where the contaminants are going and seeing whether they're not going in a bad place or not. So this is what you want to be able to do. So this is just kind of looking at some dry cleaning solvents. There was evidence that the concentration was decreasing. There was a second evidence that you have the parameters for the microbial activity to be occurring. And the third one is that you have the bacteria that are possible there. So in that particular case, we said, yeah, there is evidence. Now, the question is, of course, whether you're going to reach the decontamination level fast enough. Do we have to wait 50, 100 years to this happen or not? Or is it, are we going to reach it? So these are the questions that we always have to ask. So if you want to compare, so comparing the different remediation techniques, this is one thing, looking at life cycle assessment, looking at the whole process of the remediation, to what materials you're using, how you're doing it, what energies, and things like this. In this particular case, they compared two different technologies, doing the landfilling versus doing in situ method, which we call solidification stabilization. And so in that particular case, they saw, hey, the costs and the disturbances were very high by doing the excavation, but if you did the stabilization and so on, it was much less. So this could be considered a more sustainable remediation. So these are some of the tools that are available at this point. Another one is looking at the gold set. So the advantage of gold set now is it actually incorporates some of the social components as well. So they look at environmental, social, and economic indicators. You do the indicator selection, you do the scoring, you put in all the entry, you do a multi-criteria analysis, you get your results, and it's shown graphically. So very quickly on this one, because I see my time is really starting to go. So looking at the case studies, there was a train derailment in a peat bog. So obviously peat bogs are very sensitive. So there was a lot of petroleum there. You have, they had to do the emergency pumping of the fuel, but of course there's still, some of the fuel was still remaining. So they needed to figure out how to do the remediation of the bog itself. It's considered an ecological reserve. So they looked at three options: the natural attenuation with partial excavation, and a full excavation of the bog. So these are some of the indicators, looking at the soil, the waste, things like this. So on the environmental side, These are some of the economic indicators, looking at the net present value of the thing, the technology uncertainty, and so on. And then finally, they looked at some of the social indicators as well. The disturbance at the site and things like this would be the social aspects. And, oops, sorry, that's a little bit too quick. So basically, the natural attenuation has the biggest benefit for the environment, the economics, and the society, followed by the partial excavation and then the total excavation. However, because the regulators did not allow only natural attenuation, they were a little bit scared that the contaminant levels would not go down. The second option was then chosen, which is the next sustainable one. So these are some of the ways to increase the sustainability. They put like various floating walkways to not disturb the bog itself. They put solar panels to reduce the greenhouse gas emissions, and they minimize the damage as much as possible. So this is also a process of doing biological treatment. So the advantage of using biological is that you're really letting the microorganisms do the work for you. So you might need to put a little bit of air, which are some of the tubings, as you'll see. You have some air injection. You might need a little bit of nutrients, such as nitrogen and phosphorus, to add to the soil, and a bit of moisture. But then you can just pile up the soil, contaminate the soil, and leave it there, basically, with a bit of aeration and the moisture and things like this. And this type of process can take like 2 to 3 months, say, for an example. And then before, the regulations were that you could not reuse the soil once it's contaminated. You still had to put it into landfill. But now the government agencies are starting to be a little bit more flexible, that you could reuse the site in limited ways. So this is, so this is the facility. It's sort of in the east end of Montreal. They do a lot of hydrocarbon contamination, decontamination. And then finally, I'm getting to some of the stuff that I've been working on for a while. So I've been using, I think was mentioned before, that I've been using these biological surfactants. So the thing is with surfactants are basically washing agents. They're just like soaps. So, and also if you have a salad dressing, they're a way to help to increase the emulsification between the oily phase and the vinegar. So they can do things like that. So the surfactants that I've been using, as opposed to synthetically produced ones, are biologically produced. So they're produced by bacteria, they're produced by yeast, and they're definitely highly biodegradable, low toxicity. Potentially they could be more economic because they're very active, so you might not need as much of them. And then some of the research that I've been doing for many, many, many years is looking at how can they help to enhance the biodegradation of petroleum, removal of metals from waste and sediments and so on, remove the various contaminants from the waste, and also help to disperse oil and so on in various oil-contaminated media. So these are just the structures. As you see, it's a sugar, basically, and a lipid are the two parts of the structure of these, what we call rhamnolipids and sophorolipids. So these are two of the varieties that we've been looking at. Okay, so particularly oil sands is quite a problem. So you have a lot of these big ponds filled with oil, filled with all of these very, very small particulates that stay suspended for eons of time. So we've been looking at these, what we call miniature fine tailings, the small fraction that's underneath, and seeing what we can do to help to remediate that. So we tried to see whether we can get the particles to settle faster by adding these rhamnolipids, and we've shown that that's possible. We've also been looking at seeing whether we could also screen out bacteria that can produce these surfactants. And so we do use various plating screening methods and various detection methods. This blood agar test just shows you the clear zone, which means there's a presence of biosurfactant that's being produced by that particular strain. That was actually some work that I did when I was an undergraduate student. And so now it's still a process that's being used now, actually. So recently, we've isolated some of the biosurfactant producing microorganisms, and we put them back into the oil sands, and then we've seen some very good preliminary results that the oil can be degraded relatively quickly compared to no addition of these microorganisms at all. We've looked at combining the rhamnolipids with nanoparticles. Nanoparticles are very, very, very small, obviously, with nanoparticle size, nanometer size. And the advantage of these ones is that they're very active, but you have to keep them in the nanoparticle size, otherwise they agglomerate, and then they become useless as a nanoparticle. You might as well just have any particle there. So by combining them with our biological surfactants, we've seen it actually reduces this agglomeration that occurs. So that's been quite popular and increases the oil treatment. We've had some tailings from a mine in North Yellowknife quite a while ago. And we looked at the extraction of various types of metals, manganese, iron, and we've seen that, yes, with the sulfur-lipid, that we've seen some promising results as well. So more recently, we just got a new grant, and we were going to be looking at actually trying to extract the metals so that you could actually recover them from waste materials, and then you could be reused, say, for example, for clean tech and everything. So if you have various things like lead, copper, zinc, and things like this, being able to extract them from things that are just waste materials, just sitting around there doing nothing, then try to recover them that way. So we're starting to look at that. We've also done a lot of work on, as previously mentioned, lakes and so on. So as you see, suspended solids that get into the lakes and so on, you have nutrients that get into the lakes. This is some work of my Japanese collaborator. He retrofitted a barge there, basically, and you can see it was able to filter the water there. And then they extended the process actually to treat some of the sediments that were contaminated from the Fukushima thing. So as you remember, the Fukushima was the blast or whatever that ended up contaminating because of the nuclear plant and so on, became very radioactive and so on. So they come up with a sort of like this resuspension technique to be able to resuspend only the particles that have a high concentration of the radioactive material. And then what you would do is you would capture that and then filter it in a plant just on the side of the bay. And so this shows you the dredging equipment that they use. They did it by remote control because it's obviously very radioactive in that area, so you don't want to have people there. But they were able to, as you see, reduce the amount of radioactivity in that area by about 98%, so it worked very, very well. So we've also been trying to, so some of these stuff had originated in Japan, we've been adapting it here in Canada. So this was actually the lake that Tim mentioned before, the Lake Carroll. And so we've been doing a lot of work over many, many years on it because we've been focusing on the nutrients and the excessive amount of nutrients that are in these lakes and so on. And what it does with the geoenvironment is the sediments actually capture a lot of the nutrients. So every year you remove it from the water, but then it's still in the sediments. So unless you do something ultimately with the sediments, you're still not going to solve the problem. You'll resolve partially. So as you see, this is what we've been doing to do the water part initially. So having a sort of like floating filter. And so you can see that some of the lakes look like this, unfortunately. And we've been able to reduce the turbidity in the lakes. And then ultimately, we've been trying to do some stuff with the sediments as well. We've also been doing stuff with sediments in a yacht club. We've been taking samples there for many years. So you have a lot of the activities at the yacht club that generate, such as the paints, such as the transport of metals from an upstream metal processing plant and things like this. And so what this shows you is that closer to the surface, the contaminants are less. So you have a kind of a natural recovery process that's going on because you have clean sediments overlaying the contaminated sediments. So you have a kind of a natural dilution that's going on. And again, you can see there's kind of we've actually have more recent results, which I still didn't have time to put there, but anyway. But yeah. So this is, we've been also doing this resuspension for these sediments as well. And as you can see that we were able to get a reduction in the amount of heavy metals that are in the sediments. And the advantage of this is you don't do the dredging. The dredging is very disruptive because you're removing everything, whereas we can just remove maybe about 5 to 10, less than 5% of the overall sediments, but you can achieve a good reduction in the sediment and concentrations. More recently, we've been looking at basically stabilization techniques. So there are a lot of carbonates and things like this that are naturally found in your soils and so on. But a lot of people are starting to work now on using what we call microbial carbonate precipitation. So ideally, you can precipitate and stabilize these soils. And so this is actually sand that's piled up here. And so you're basically gluing together the soil naturally. And so most recently, we've been doing work with some waste material, doing the same type of process, and we've seen that we can actually use it to sequester the carbon dioxide in the air. So we've had almost up to 99% removal of carbon dioxide from the air into these waste materials. And then last aspect that I would like to mention is that obviously the social dimension is very important for doing the engagement and so on, for being able to realize the reduction in contaminants and working to reduce the effects of climate change and so on. So Indigenous people are basically, as we've mentioned, have very, very good strengths because they're very keen observers. They understand, they are one with the land and so on. So they're able to have a very good understanding of some of the changes that are going on, particularly under climate change right now. So they're calling for urgent needs, and we have to listen to this call. And obviously to work with them on, we've heard with the Truth and Reconciliation Commission, be able to work with them and building these respectful relationships with Indigenous communities and so on, and get the informed consult and do the research with them, and to be able to allow them to have good training and so on, but also to be able to gain some of our understanding from them as well. So we need to develop research and policies with Indigenous and Western knowledge working together in what people have called this two-eyed seeing way of things. So this is very important, I believe. And also, make sure that we have all of these connections with the health, the wellness of the local, regional method wells and areas and so on in this One Health kind of scenario where we look at things, not just they don't think what's going on that particular thing, but we look at things a lot more holistically. So engage people right from the beginning, not just at the very end, and make sure that it's a continual process through no matter what steps we do. So I'm a little bit over time, but not too bad. So conclusions, we need to do a proper management of the geo-environment. We have all sorts of impacts, of course, such as depletion of the resources, all of these problems with waste management, decreased soil quality, the depletion of the agricultural lands, deforestation, and contamination of water. We need to have much more sustainable methods for dealing with this soil, sediments, and so on. Particularly, don't put the contaminants in the first place, try to remove them and try to reduce the contaminants getting into the environment, using sustainable remediation techniques to do so, using the natural processes as much as possible, and as I say, using techniques that have a low impact on the environment through their emissions, water, energy, and so on. And of course, we would like to restore the habitat as much as possible to the few, and of course, have the engagement of the communities. So, yeah, so I think that's pretty much the same type of thing. So I would like to do my acknowledgements. So this was at a recent seminar I did in Montreal, the geo-environmental. So you can see many of my students and collaborators here in this picture. So I would like to obviously to thank all of my collaborators, my students over all of the years. I thank obviously the Royal Society for giving me this opportunity. I thank the funding agencies, the Fonds de Recherche du Québec, the NSERC, our industrial collaborators, Titan, Agnico Eagle, and Rio Tinto are also collaborators on us on some of the other projects. And finally to Innovation 7 for their help from them in our doing the Indigenous engagement part, and of course for being the moral support today. 2 of the members are here today, so I appreciate very much that as well. And I also finally want to thank, most of the stuff came from a lot of my books, but particularly the Sustainable Practices in Geoenvironmental Engineering, and my collaborator, obviously Masa Fukui is the Japanese collaborator, but the last author is my PhD supervisor. He is 96 years old, and he still helped me with this book, so he's been such an inspiration, so I really thank him as well for all his help throughout my career. So I thank you for your attention. If you have any questions, si vous avez des questions, c'est un plaisir de répondre. Merci beaucoup.
Thank you very much. Yeah, there's so many topics you touch and so many examples of environmental damage that I'm sure we'll have many questions. We'll start here.
Oui, Christine Tapolet, Université de Montréal. I'm a philosopher, so my questions are really not good.
Okay, I'll try.
The first one is a yes or no question. I've seen this landfill, open-air landfill with bears feeding on it. Is it even legal? Like, yes or no? Probably not. Killarney or Georgian Bay. The real question is stones. You mentioned soils, but it seems to me that like stones play an important role as well. I was like, broadening the picture, I was wondering about stones.
So, yeah, I mean, stones are just, because basically if you're looking at soil, it's basically rock to start off with. It gets broken down into smaller and smaller bits and pieces. So stones are definitely part of the process. They just happen to be larger. Sometimes they have less influence on the contaminants and things like this because they're so large. The surface area is not so big, so they have less influence. So particles like clays will have much more influence than stones. So typically stones and rocks are removed usually if you're doing an ex situ process. Yeah. The Canadian Shield? Yeah. I mean, well, it depends on the place, what exactly is in a particular place, but yeah. Things vary so much with soil. That's one of the take-home messages. It's much more complicated than water. Yeah.
Jacob Pendergrass from Toronto. I loved this presentation so much. So interesting, very inspiring. I live in the part of the city that's close to the Portlands, where there's been a major soil remediation and sort of a deindustrialization project, which I think has been very inspiring to everyone, particularly watching the renaturalization of the mouth of the Don River and sort of trying to undo a lot of that, sort of 19th century industry. I'm curious what your position is on this other trend, which has been growing in popularity in cities, of daylighting streams, where buried streams and rivers are taken out and kind of re-exposed to the way they had originally been. I think people like the looks of this. It feels like you're undoing something that was unnatural. But is this actually a bad thing in terms of runoff and water contamination?
I'm not quite so familiar with this, but I know some things cities do in the way to help, maybe not necessarily are helping. Sometimes, I mean, people have been they've been building these sponge areas and things like this in cities, I think, to handle the runoffs and things like this. This seems to be working because it's kind of a way to simulate some of the natural processes. So I think in that way it's helpful. But sometimes if you're destroying some of the stuff that's already there, it's not necessarily a good process. So just in terms of like destroying a lot of the wetlands and things like this that are the natural places of protection, that's one of the biggest probably impacts that the cities have, I think, by doing all of these stuff and that help actually in terms of flood controls and things like that. Yeah.
Before I give to others, I have my own question. So, talking about Toronto, talking about you talk about the nuclear reactor in Japan. Mm-hmm. So, Canada, Atomic Energy Canada, is moving forward to develop these mini nuclear reactor. One will be near the nuclear reactor in Ontario, in Pickering, but the plan is to put this all over Canada, including in the north. So you talked a bit about this, but is this something that if you put it on Pergé-la-Sol, that is melting, we wonder what this will go and if the government does a good job at this or not, It's a direction for Canada or not.
I don't know, are you asking about the nuclear? Is that what you're kind of more looking at?
So is scientists in your field are involved into positioning these future plant or current plant of Atomic Energy Canada so are you do prevention before any of those things happens? Because obviously you're the right people to study this, right?
Yeah, so. I mean, if you're looking at the nuclear industry, the waste management is a huge issue because what do you do with and this is still a topic that people are debating and so on. I know there are just some researchers in the RMC.
We're just all focusing our trouble to you.
Yeah. So, but I mean, a lot of the developments of the new systems that are coming, the advantage is that we're going to be generating less waste. So from that point of view, I think some of these modular and small systems can be better in terms of what some of the the nuclear systems have been in the past. So, but unfortunately, nuclear is actually one of the best energy sources because they're so efficient. It's so efficient, and it's but obviously it has to be managed properly. So yeah, there are definitely researchers in my field that are working in this area. Yeah.
Good afternoon, Robert Boilly, incoming president of the Academy of Science. Water quality is a very important topic. Here around Montreal, every summer, there are many articles about we should not swim in the river, or someday we can swim in the river because it varies. But we also have lakes, a lot of lakes in Quebec.
Yes.
And there has been a problem in the past years about algae bloom. Mm-hmm. But other times they say it's not really algae, it's a bacteria.
Cyanobacteria, yeah.
So it looks like algae, but it's not.
It's not an algae, no.
So which one would you say is the worst for the environment and the most difficult to control?
Well, the algae have a more aesthetic issue because you have a green lake, like one of the pictures I showed you there. So it's probably not nice to, but
it depends which color you want, blue or green.
Yeah, but the problem is that if you have the cyanobacteria, they actually can produce toxins, and this is the problem. So some of not all cyanobacteria produce toxins, but some of them do, and so this is something that has to be monitored a little bit better, the amount of toxins, because the toxins are not, people are just maybe have some rashes and things like this, but for animals like dogs, if they're drinking the water, it can be fatal for them. So the cyanobacteria are the biggest problem. So actually, one of the green place that I showed you was we had some citizens that had their green there, so we went to their lake, took some samples and so on, and we did some analysis of the different cultures, and there definitely were there were definitely cyanobacteria that most likely could be producing toxins. We don't have the method in my particular lab because you need a very high level of clearance to do the toxin analysis in the lab, so we didn't do the analysis, but definitely that particular lake was a particular case where there could definitely have been some cyanide. So basically we tell them, don't go in the lake, don't put your animals in the lake, and just be very careful. Yeah. Yeah.
Thank you very much for your timely and inspiring work. Peter Liu from University of Ottawa. And this last week we heard, the current government really actually putting out a lot of infrastructure projects, and the latest group is in fact all on rare earth, mineral extraction acceleration, right? And so, that kind of poses the question, are these, mitigation strategies actually planned in as we are in a hurry, compete on the global economic front? And you have a number of really innovative, solutions. And I wonder whether, in this type of situation, whether this could be opportunity to kind of test some of these, in the real world as
it definitely could be. I mean, my issue, I think, sometimes is just because it's a mining project doesn't mean it's bad. We'll say this for one thing, but if they don't do the assessments properly and they do it too quickly and too whatever, then we could have some issues in the forward. So this is my worry a little bit in this sort of speeding up of the impact assessments that are part of these projects. So these really have to be done properly, and so the systems have to be designed properly so that we're going to be mitigating any potential issues. And hopefully, if there are any issues, I can be of help.
We're coming to the end of our things. We have 2 more questions, and I'll
ask after the presentation, but okay.
Okay,
sure. Sure. I'm a chemical engineer with kind of common research interest, so you kind of touch, the optimization and screening of biosurfactant and combination of nanoparticle. So I was wondering what kind of the procedure is followed to screen and optimize biosurfactant and combination of nanoparticle.
Well, we look at all the various conditions and things like this, pH, concentrations, ratios, and obviously to see what affects in the future, whatever. I don't know, maybe we can talk a little bit more. So it's very...
So these are commercial, you produce this by commercial means?
We actually produced our own nanoparticles in the lab.
But
They're basically iron and copper based, so they in theory should be much less toxic than potentially some of the
have you used them really in the nature so far, in the real conditions?
We have not done them. We've just been doing them in the lab.
Already that seems to be a very... expensive solutions, but
possibly.
we could talk.
Possibly.
So one last, and then from a chemical engineer, so we cannot have better than that to finish the evening. So
Great, thank you so much. I'm from Western University, so I am also doing a little bit of water contaminations and dispersing oil in water, but. Today, my questions is probably quick for you. I was wondering, because you're working on the contaminants of heavy oil, heavy metals, and other contaminants. Yeah. So I was wondering, do we have a big data or a map of those contaminants across Canada, so we can warning our people where can go, where cannot be going, and doing their stuff? That would be probably important for a guidance for common people.
Yes and no. There are a lot of inventories, as I've shown you a little bit, but sometimes they're very vague in terms of what contaminants are there, and it depends, so sometimes you can see what's at that particular site, and other times you cannot. Sometimes they're but you never see the levels and things like this. This is not very publicly available. So
it's very, like you said.
It's varied, and it depends. The problem also with land is it depends on who owns it. Right, so federal have one set of rules, they'll have one set of guidelines to use, the provincial will have another set of guidelines, and they have different procedures as well, municipalities and so on. So
a great example of this is the Canadian Army. So all the bases are very much contaminated, so that's one thing. Another thing, I talked to my colleague from Prince Edward Island on erosion also, and they also satellite monitoring, and there's much more coming in, and everybody will have this little drone to follow their principal chemicals. So all of this to say, you put really in front of us very difficult situations, but many good scientific solutions. And I'm thanking you for bringing this up, and the Royal Society is well positioned with many of us can maybe help in producing some ideas. So thank you everyone for being here, and we'd like to thank Dr. Mulligan for her talk, and wishing you a great afternoon. Thank you.